This is fundamental problem 15-9. In fundamental problem 15-9, the 5 kilogram block A has an initial speed of 5 meters per second as it slides down the smooth ramp, after which it collides with the stationary block B of mass 8 kilograms. If the two blocks couple together after the collision, determine their common velocity immediately after the collision. Even though this problem is in the chapter 15 where we're doing impulse momentum, we can still use the conservation law from chapter 14 for work energy in order to help us solve this problem. So first of all, when you see a block A sliding down the ramp and read that the ramp is frictionless, this should remind you of what we did in chapter 15 where we have objects sliding on frictionless surfaces. So we have a force of gravity acting on block A, and we also have a normal force acting on block A, but since the normal force is always perpendicular to the direction of motion for block A, the normal force is not doing any work. So the only force that is doing work on block A is the force of gravity. And rather than looking at the work done by the force of gravity, we can look at the potential energy for gravity. So we are free to do that, and we should recognize this as a situation in which using work energy would be an easy way of finding the velocity of the crate at the bottom of the incline. Furthermore, if you were going to try to use the impulse momentum relationship to find the speed of crate A when it reaches the bottom of the incline, because the impulse momentum relationship is a vector equation, you would have to look at two different components for the motion of the block here, and you could solve it that way. However, it would be much more complicated. So since we can use work energy to solve this problem, that is what we are going to do. And we're only going to use work energy up until the crate gets to the bottom of the incline. So we have not talked about what happens when objects collide yet, but we have not learned how to use work energy in cases where objects collide. So that's coming up later. For now, we're just going to use work energy to find the speed of crate A when it reaches the bottom of the incline. So we're going to break this problem up into two parts. First, we find the speed of the crate at the bottom of the incline, and then we'll find the common velocity of the crates after they couple together. So I'm going to use work energy to begin. Okay, now I called the initial velocity of crate A when it starts at the top VA0, and I'm going to call the speed that I'm looking for now, which is the speed of the crate at the bottom of the incline, VA1, and that means I'm looking for V2, which is the speed after the crates couple together. So in order to find the speed of the crate at the bottom, I'm going to use the work energy conservation law, where, as we already discussed, the work done by non-conservative forces is equal to 0. So that means my initial kinetic energy plus my initial gravitational potential energy is equal to my final kinetic energy plus my final gravitational potential energy. Now, I can set my datum at the bottom of the incline, which means my initial height is 1.5. So I have for my initial gravitational potential energy, the mass of crate 8 times g times 1.5. Since the kinetic energy is 0, this is what I have on the left-hand side of the equation. And on the right-hand side of the equation, I have my kinetic energy of 1/2 mv squared plus any gravitational potential energy that I have, but the crate is now at the bottom of the incline, so gravitational potential energy is equal to 0. So initial gravitational potential energy is equal to 1/2 times the mass times my velocity squared. And I'm looking for the velocity. This is VA1 at the bottom of the incline. The mass cancels out, So I have VA is the square root of 2 times G, which is 9.81, times the height of 1.5. And that gives me 7.378 meters per second. Now that I have done that, I can look at the collision. For the collision, I am going to use the impulse-momentum relationship, which we have here. And I want to check to make sure that there's no impulse if I have the system of the two crates when they are colliding together. I have the force of gravity acting downwards. This is for the system, so that would be mass A plus mass B times G. I have the normal force acting upwards. And I was told that the ramp is smooth, and so there's no friction in this problem, so there are no forces acting on the system as a whole in the horizontal direction. You do have the force of crate A acting on crate B, and the force of crate B acting on crate A, but by Newton's third law, those forces are equal and opposite, which would give you a total impulse of 0. So looking in the horizontal direction, the impulse is 0, and we can solve this the same way that we solved the previous problem. Crate B is at rest to begin with, so the total momentum initially is just coming from crate A. That's the mass of crate A times the speed of crate A when it reaches the bottom of the incline, which we solved up here, is equal to, since afterwards the two crates are moving together, the total mass of the system is MA plus MB, they're both moving together, times the velocity which we're looking for. Since they're moving together, we'll just call that B2 for both of them. So I know the mass of crate A is 5 kilograms, the mass of crate B is 8 kilograms, so this is 5 plus 8 times V2, and crate A has a mass of 5, and the speed is 7.378 before the collision. So I can solve this for V2, and I get 2.84 meters per second. Rather than looking at equation 15.3, you can look at equation 15.6, which was for a system of particles. In equation 15.6, they have the sum here for the sum of the momentum for each particle that you have in your system. So this would be, if you write it out, mass A times VA1 plus mass B times VB1. VB1 isn't 0, and so this would be 0, and that would give us the same thing that we have up here. And then afterwards, after you check to make sure that the impulse is 0 for the system, you sum up the momentum for each particle in the system. So that would be, MAVA2 plus MBVB2. So you could write the equation that way as well, but VA2 and VB2 are equal to each other. So you could also just call that MB times V2. So equation 15.3 and equation 15.6 are essentially the same. You can use equation 15.3 when you have a system of particles, and if they're both moving together after the collision, you would just do the total mass times the speed that they both have. And in the two problems that we looked at, fundamental problem 8 and fundamental problem 9, we only had one object moving beforehand, and so one of these was always equal to 0. And that concludes fundamental problem 9.